All right, guys and gals, we're going to get started here in a moment. So please take a seat. Remember the 5th of November. All right. You can sit anywhere you want. It doesn't matter as long as we get angry, right? Cool. Well, thank you all for coming to Austin Deep Learning. Hope you could trek through all the water that fell last night. So just a quick show of hands. Whose first time is it here today? Okay, 50-50 like usual. So if you parked in the garage, you just come up to me after the event. I have these nice parking validations. It takes it down from like $50 to $8. The contingency is you must have come after 6 p.m. and you have to leave by 8 p.m. or 10 p.m. Sorry. So we usually meet here in Capital Factory. The room tends to change, but we meet here usually on the first Tuesdays. We do not have one next month. We take off December, July, but we come every month on the other months. So coming back up on January, we were focused more on research and new applications. It's an open discussion, so it's bi-directional. We're going to have two speakers here today, Matt and Orlando. Matt's with Amazon, and Orlando's with his startup Toolhouse. So if you have any thoughts, any insights, raise your hand as well, not just for questions, but also for questions if you want to have more clarity on something. This is a long-running group. It's the longest-running AI group in all of Austin. So we are on event 169 today. So it's an 8-year group. Thank you. So we've been going strong for 8 years. And so there's some people in the community here who want to make an announcement. So John and Jake. I'll give you all both the mics so you can talk over each other.
All right. Thanks, Rakshak. Hey, everybody. My name's John Boxstans. I'm here with Meta. Here because at Meta, we believe strongly in an open source approach to AI. And I'm here to meet you, especially if there's anyone here who's using Llama. I'd love to get to know the ways that you're using it, how you're finding value, because we're really passionate about building community. And as part of that, we're partnering with AITX and really glad to be here with Jake.
Awesome. Thanks, John. What's up, everybody? My name is Jake O'Shea. I'm one of the main organizers of AITX. We do a monthly event meetup, most focused on connecting local engineers and big tech companies with local startup founders and people building technical products. So we host a monthly meetup. We host a bunch of other events. Next week on Tuesday, we have Orlando, who's going to talk to you guys later. He's hosting a hackathon, so just trying to kind of provide some infrastructure to make sure everybody knows what's going on. And really excited to partner with Meta on this Llama hackathon. It's going to happen in about 2 weeks, November 22nd through 24th. On the 22nd, we're going to host a kickoff, which is going to be really nice. We're going to have some demos from local AI companies, some use cases for Llama. Some people from the main Llama team are flying in to talk about how they're designing and building everything. And that'll be at Meta's really, really nice offices downtown. So really excited for that. You can sign up for that on the left QR code. That's just the kickoff for the hackathon. Right, so that's where we'll introduce kind of the judges, the criteria, and really just like a big celebration before the main event, which is the next morning through Sunday afternoon. So Saturday morning through Sunday afternoon, the Austin Llama Hackathon, that's going to be right here at Capital Factory. So we're targeting like 150, 200 developers. Most of them will be here locally. They'll all be building products with Llama. We've got some really, really interesting judges. I think we've got the CIO of the city of Austin.
We're working on it.
We're working on it. We've got a lot of really great judges locked in, some really cool prizes. Just really excited to see what the community comes and builds. So yeah, if you're interested in checking it out, if you want to come for the kickoff, eat some great food, if you want to come for the hackathon, build something really cool. If you're here, it means that you're probably pretty knowledgeable about the technology and probably can build some cool stuff. So we'd love to see you at the event.
Thanks, everyone. So just to summarize, if you're using Llama, I'd love to get to know you, and feel free to reach out to me after the event too. So I'll connect with you for sure. Oh yeah. That is a good question. I actually don't know for sure. It's a lot. So many, I don't know how many are around me, but it's like, I think thousands. So there's a lot of us. Love to get to know you if you're using Llama, or if you just want to learn more about it. And please register now for the that reception on the 22nd and the hackathon on the 23rd and 24th. So thanks for having us.
Yeah. I've also worth mentioning, Llama or Meta is handing out Llama Impact grants. So if you build something with Llama, you can get non-dilutive grant funding from Meta to take it to the next level. So they've always been really great advocates of the open source community, and this is just kind of another reason that they're so supportive. So thank you, John.
Great. Thank you.
All right, so today we're going to do two 30-minute talks. Matt's going to do the first one, so if you want to come up. And if you want to get the paper ready, because I know a few people tend to read it ahead of time, but it's good to just reference. So if you want to scan the QR code, I'll leave it up here for a few more seconds. Okay. Okay. All right. Take it away, Matt.
Thank you very much. Can everybody hear me okay? Excellent. All right. Well, thank you very much for the opportunity to speak here. It's really very exciting for me as well. My talk today is mainly going to focus on how you can use more test time compute to improve the accuracy of your large language model outputs. Now, in general, talks on the internet tend to do better when you have like a pretty big claim, you know, some kind of very hyperbolic just claim that you're trying to make. So I subtitled this, How to Get in Shape Fast Large Language Model Edition. So specifically what we're going to be going into is this DeepMind paper. You guys should all now have that on your phones. The point of bringing this up is to say these are not novel ideas to me. This is specifically going to be the result of a couple weeks I spent diving deep into this paper. And another point is that I am not coming up here to say I know everything. We have an incredible density of very, very smart people in this room. So I'm going to ask you, if at any point you're confused about something I've said, if at any point you want to add something, or, you know, especially if you think I've said something wrong, please feel free to just cut me off, yeah?
I don't want to jump in too far, but one thing I'm concerned about is the reward model. Because it's similar to reinforcement learning. Maybe when you get into it, talk about it more in a broad sense. I can cut back to RL.
Sure. Yeah, of course. Yeah, so basically the way the talk is structured, that's actually a great segue, is into these 5 pieces. I'm going to start off with a high-level idea of how this paper was kind of presented, the big ideas they're going after. Then I'm going to dive into the 2 ways that they have put forward to improve your model's accuracy, verifiers, and then modifying the proposal distribution. We're then going to go into basically how you're going to use both of these to get the best results. And then at the end, should we have time, we'll have a discussion among the people here. So, without further ado, how many people in here have used the O1 model from OpenAI? Okay, excellent. So a good number of people have personal experience. What I'm showing on the screen here is the chatbot arena comparison for all of the different models. And you can see that when you compare the OpenAI GPT-4o Mini, especially from 2024 July, you can see that O1 Mini is a fairly substantial increase from that. And when you go into the blog post from OpenAI, part of the reason that they say it does so much better is it's taking more time to be able to think through its answers and thus give you a response that's more likely to be accurate. So, to me, when I read this, what jumped out was that we're really expanding on what's been known to be working. So another quick question, how many people here have used or even prompted using chain of thought? Okay, a good number. just in case you don't know, the basic idea is that when you are prompting a large language model, you tend to get better results when you ask it to think through what it's doing. So on the left, you can see we're prompting it just to give us straight an answer. And on the right, we're asking it to go and show us the steps. So you can see that on the right, you get a better answer, and this in general has tended to be true. So the high level idea here is let's really bet that this is going to continue to work. Let's have the large language model continue this. And so to give you the bottom line up front, in terms of cost savings, what you're seeing here, and we'll go into the graph in more detail later, so don't worry if you don't understand all of it. What you're seeing is that when you use these methodologies, you're not only going to get higher accuracy, but compared to other people who maybe don't have your data and aren't able to have the same accuracy methods that we're going to go into, you will end up having a lower cost structure. And, you know, I think everyone understands if you can do things other people have to pay more to do, you are going to outcompete them. So hopefully that got your attention. The key ways that they say that we should go about trying to improve accuracy is with verifiers and modifying our proposal distribution. And it's helpful to think about a large language model, at least for these two ideas, as giant distributions. So with our verifier, we're going to have one distribution for one prompt. And the basic thing that we're going to be going through is finding which sample in that distribution is going to give us the correct answer. We're exploring this one distribution. Now, modifying our proposal distribution, on the other hand, we're going to generate a number of different distributions, and we're going to pick the distribution that gives us the highest probability of having the correct answer the first time. So, before I go into the details for verifiers, are there any questions from the group about the high level here? Yeah, so the basic idea is that each of these distributions is a possible answer the model could give you for that specific prompt. So let me use my mouse here to kind of demonstrate. You ask it a question, and it could give you any of these answers. LLMs are non-deterministic when the temperature is above 0. So when you have multiple proposal distributions, what we're saying basically is that we're going to ask the model multiple different prompts. Question. That's an excellent question. I'm going to go into more detail in a second, but basically, we're going to ask it the same question, and we're going to be modifying the prompt we're giving it to try to get the correct answer. So to kind of go forwards then, for verifiers, this is the basic image we're working off of. What we want to be able to do is have the model understand when it's going in the right direction. It's not very useful to go through this distribution if we don't know when we have a correct answer. So you can go about this a number of different ways. You have large language models as judge is a very common one. But specifically in this paper, they followed the methodology that an OpenAI team had begun in their paper, Let's Verify Step by Step. So it's very helpful to understand this idea by going through the data. You can see here, it's given a math problem, and then all below it is a number of step-by-step ways that you can get to the correct answer. The critical piece is the 3 faces you see on the left side here. You have a smiley face, the mid face, and then you have the frowny face. So the key thing that you're going through is you're going to be telling the model each step if it's on the right path or if it's on the wrong path. So this is coming from PRM 800K, and specifically this was done by humans. OpenAI paid them to go through and say right track, right track, right track, I'm not so sure, and then wrong. So the basic idea, and you can see it in this example, looks like the text is a little too small to see here, but to kind of explain what the image is showing, you have the question, and then all of the text beneath it is going through the logic it's going through to try to answer that question. And so when it's in green, that means we think there's a high probability it's on the right path. And then you can see for the response on the right, we have certain text that's in red, certain text that's in yellow. And so this is signaling that the separate model, our process reward model, is telling us that this is probably making a logical mistake. Now, the data here is going to be trained for a model that'll give us a probability of if this is correct. So the basic idea is that on the left and on the right, we can put these both into our model, and it will give us a probability for each of if one is correct or if the other is correct. And we can then use these probabilities to directly compare them. So if you come back to the idea of the verifier, we now have a way that we can go through each of these different responses. We have a probability of how likely it is to be correct. And you can say, okay, this one is 0.98, this one is 0.97. We're going to go with the one that's higher. Are there any questions about the
How are
PRM?
you computing the probability that it's correct?
This is from the process reward model, the PRM. So they're training a separate model to be able to tell them if it's on the right path.
So that was trained on label data, and then now it's predicting on unlabeled data. Okay.
Exactly, exactly. So this kind of leads to an interesting problem. When are you going to check if your model is correct? There's not really one correct way to do this. So starting off, we have a relatively straightforward way, best of n. So yes, you guys can see clearly that image. Here, we basically tell the model, I want you to generate 4 full responses. Once you've done all of that work, I'll put each full answer into our process reward model. And from there, we'll get back our probabilities and we'll pick the one that performed the best. So compared to some of the other models or methods that you're going to see, this way of finding out which one we should return to the user is the least additionally expensive. Now, does anyone see a potential problem with using best of n? Exactly. So in the example here, we're picking one of them that's the most correct. But if you see in this example here, you could make a logical mistake about halfway through. And then because of that mistake, you're now on the wrong path. The final answer is going to be wrong. So for best of n, we're not going to be able to catch that mistake. So this brings us to a different way, which is beam search. The idea, or actually, how many people know about breadth first search? Okay, excellent. So beam search is a kind of extension of breadth first search. Rather than being exhaustive, where in breadth first search we're going to consider every possibility, beam search says instead, I'm only going to focus on a very small subset of these, and I'm going to go all the way for these. So in the example here, we have a value n and a value m. With n, this is telling us how many samples we want to consider every time we're going to basically check the work of the model. And then for m, that's telling us of all of the ones that we're considering, how many do we continue on? So in the case of n, we're choosing 4, and in the case of m, we're choosing 2. And so the reason that this is meant to be more effective is that as you go step by step, you can check the work, and then if you're going in the wrong direction, you no longer continue going forwards. Now, the last piece the authors looked into is look-ahead search. And so this is meant to prevent the model from going mostly in the right direction, but then kind of falling off a cliff. So this is an extension of beam search. We're again going to be stopping at certain points and then considering a few of them and then going through with even fewer. However, when we are putting our answer into the process reward model, what we are doing is sampling ahead. So you set your temperature equal to 0, so there's no surprises, and then you go, in this case, k tokens forwards. And the basic idea, or you know what, I've used that phrase too much. So from a high level, the important thing here is that this gives you the most amount of information so that you can make a good choice about which branch you continue on. And so the big question now is, we have the theory for these searches. How do they actually compare to each other? I don't think I'll have the time to go into the right graph. So if you're curious about that, please come find me afterwards. But to go into the left one specifically, we're comparing all the different models based on the accuracy of the response they give, and then also based on how much compute we give them. So generation budget is how many full responses we allow it to generate, 2 to the 5, meaning 32, etc. So the important piece here is we can see that look ahead really underperforms. Even though it's going to be the most computationally expensive, we don't see it breaking away from the other ones, and given its higher cost, it really doesn't seem to be justified. Now, conversely, beam search does fairly well, And then most interestingly is the best of n, which we considered to be most likely to give us the wrong answer, actually in the empirical study here is doing very, very well. So what the authors do for the rest of the paper is they mostly focus on using best of n, just given this data here. So that is from a high, yes, please.
Yeah, so isn't it the same amount of compute per strategy? So the look ahead actually is at disadvantage because it's more computationally expensive. What do you guys do that?
That's so like basically to repeat the question, if you're going to keep the compute the same for all of them, wouldn't look ahead be at a disadvantage? I'm not sure I fully agree with that. So if you have the same amount of compute for each of them, but one of them is more expensive, it doesn't mean that it should pay off only at higher levels, right? If you're still spending the same amounts, I would expect it to be a fairly consistent comparison. Is there something I'm missing here?
I mean, on that graph, they're setting 2 points as generation budget. They're comparing it for apples to apples, right?
Yeah.
That's what it is now on the graph, on the left. But my question also was, so what's the step in the terms of, is it like the full generation that they do the whole comparison, or they do just a set amount of tokens?
So it should be the full response. And to be clear, in the paper themselves, they don't specify that exactly. This was my interpretation of it.
Because they could just say that adding 1 more sentence and stop whenever the parachute comes.
Uh,
I don't know. I mean, it just seems like, because from the other pictures you were showing us, you were highlighting the different steps.
right.
That's what I don't know.
So like in other words, the question is here, you have the different steps that we're going through.
So each one is, it seems like it's just a sentence, so it seems like that would be a full generation, but it could be that they just maybe stop or do a parachute run. So they don't know what it comes.
So this is a piece that's actually, to me at least, not terribly clear in the paper. When you do have this beam search, you want to be stopping it at a point that kind of makes logical sense, right? If you stop it, for example, in the middle of a sentence, it's a little bit more difficult to know if you're going in the right direction. And to me, this is somewhat unclear. I would imagine that if you really get this working exceptionally well, that would be a part of the secret sauce, so to speak. Cool, but are there any other questions then for the verifiers? Mhm.
In this graph, you want to be up and to the left, right? That's more accurate and less budget.
Yes. So the math test accuracy, all of the questions here are mathematics related. So there's a guarantee that if the answer comes out, you can verify that it's correct. And then generation budget, yeah, exactly correct. Okay.
But the top point, orange, is as efficient as like the first, second level. So they get it bigger. It's just you have more budget, you can get the results. You cannot say that one is better than the other.
Yeah, I think that's fair to say. When it looks, put simply, with beam search and best of n, we're not seeing that one is clearly better than the other, but in terms of the compute for look ahead, it does seem clear that look ahead is underperforming. Or at least, logically speaking, we would expect look ahead to be significantly above the rest for the investment you're having into it. So to move into the proposal distribution, this is coming back to your question from the beginning. The question was basically, you're going to have a number of different prompts, and if I'm understanding it correctly, how are you going to be changing the prompt so that you pick the best one? That this seems to maybe cause some issues. So from what we're looking at here is fine-tuning our model so that there's a certain format it's always going to use, and it will understand when we make modifications to it. So our data set starts off with a question here at the top, and then randomly we'll pick between 0 and 4 wrong answers to put into the context. At the very end, we have our answer, and when you're doing your fine-tuning, what you're doing is you're training it. The given is question through the last wrong answer, and then you're training it to get the label of the correct answer. Now, the basic thinking is that when you are going through all of these wrong answers, the model is able to see the wrong steps and modify. So in the same way that for a person, if you point out where they've made a mistake, they're able to learn and go eventually to the correct answer. We're applying this thinking here. If the model is aware of where it's gone wrong, it should be able to find the right answer. And so based off of this thinking, we're going to make sure that the last wrong answer is the closest to the correct answer. Now, the way that they do this is, in the paper they don't specify exactly, but I took it to mean that it was mostly edit distance, so a Levenstein kind of thing, where you're looking at how quickly you can turn the wrong answer into the correct answer using character subtraction, addition, or modifications. So with this, what you have to do is generate all of these answers for your data set. And so in addition to using these generation tactics for our fine-tuning data set, we are also going to use these later on when we are having our model itself trying to give correct answers to the user. So these come back. You have one strategy, which is sequential sampling. And this is perhaps the most straightforward. You have your question, and then you have the large language model try to get the answer. If it's wrong, you take that wrong answer, put it into the context. This would now be answer 1, and then you have it run again. Fails again, okay, that now goes into wrong answer slot 2, and then you try it again. This way is the most direct because this is how you would perhaps expect a person to do it. You have a try, if it fails, okay, you now know what's changed, and then you can try again. The problem, and the reason the authors didn't use this for their fine-tuning, was that it's much more expensive to do this. Attention is quadratic scaling. So that means that as your prompt size gets bigger and bigger, it's going to be more and more expensive to generate. They also had to generate a huge number here. I didn't go over it, but basically you have 64 answers you're generating for every single question. So I believe they had a couple, on the order of a couple thousand that they were trying to generate here. So the amount of compute was non-trivial. What they did instead was parallel sampling, where you have a number of instances of your model running, you give all of them the same question, and then the output that they give is going to be what you treat as the answer. So here, when they're generating their fine-tuning data set, they have 64 answers. You filter to make sure that you only have that last answer as one of the correct ones. And then the way that you fill in the ones here is from all of the failed ones. And this is meant to simulate what would otherwise be sequential sampling. Yes?
Basic question here. Are these annotated, or like how do they know it's correct?
That's a great point. The way that they know it's correct is the verifier.
So they're assuming that that model is correct, basically. So
Yes.
auto-labeling is using the model.
Yes. And so that's actually a great point for what we're about to get into here. Basically, what you're seeing on the screen is that as you have more generations of the model, you're getting higher and higher accuracy. Now, remember that the model was only fine-tuned to expect most 4 wrong answers. So the way that you're modifying the prompt here is that if it's wrong, you're putting it into the context. And then you have to purge the ones that are now too old to still be there. So you have 1, 2, 3, 4, you get wrong answer 5, you're gonna get rid of wrong answer 1, and now you're gonna rerun it. And you can see from the shape of this graph here that in general, you are getting a fairly good return for more generations up into arguably 20 or 30. Now, there's a logical problem here as well, namely that you don't want to correct a correct answer. So we've fine-tuned it to expect that anything that appears in answer 1, 2, or 3 is going to be wrong. And to your point, when you're using the verifier, there is still a chance that this will give you a false positive. It'll say this is wrong when in reality it's right. So we don't want the model to sit back and say, well, the correct answer was wrong, so let me go even more in the wrong direction. And they found that roughly 38% of the time, this is what would happen. And 38 is a far too high percentage for us to be comfortable. So what they did was they put the verifier into the process for selecting the correct answer. Now, I'm running out of time here, so I'm not going to be able to dive into all of these individually. If this is something you're interested in, please find me after and we can go into more of the details. But suffice it to say that what they're showing you here is that there are different ways that you can connect your verifier into this fine-tuning model. And so the most important piece is that you are going to use these two strategies to attempt answers to different questions. If you think about it from a high level, if a question is very, very difficult, you're going to use a different method of thinking than if it's very simple. And so if you're aware of this, you can change the way that you're applying your test time compute. Sequential versus parallel thinking, you can think of as either going very, very deep into one very particular type of reasoning. This would be your sequential. Or you have a high-level idea of where you might want to go, and you try a number of different things. This would be your parallel. Both of these strategies work in some cases and are abysmal in others. And so the key here is that if you have enough information to know how difficult the question is, you can apply these different methods of thinking to be able to have the best shot of answering the question correctly.
Is this like Daniel Kahneman's book?
Oh, the
system
thinking fast and slow kind
Yeah,
of thing.
yeah. So system 1, system 2.
I think it's possible. You can say it's related. Yeah. Yeah, gotcha. We're almost near the end here. So the key piece, and this is that same graph from the very beginning of the talk, is that when you are using these methods together, you're able to get the same level of accuracy with our method that you would require 4 times more compute on these other methods to achieve. So I'll explain this graph in detail here. With majority is we're using basically a vote. You generate X number of samples, whichever ones agree with the most, that's the one that you're going to give to the user. That's the dotted lines here. The straight line is we're going to be using best of n with our verifier. In addition to that, you can see that we have here parallel compute, we have compute optimal predicted, and compute optimal oracle. And so these two, the compute optimal ones, are based on figuring out the difficulty of the question and then choosing the best mixture of parallel versus sequential thinking. So in red, you're only using parallel reasoning, and then in orange and blue, you're using a mixture of parallel and sequential reasoning to come to the best answer. And so to compare these apples to apples, let's pick the one here after you've generated 32 samples. You can see this level of accuracy is roughly at 35%. And then if we compare this then to using our methodology, you can see that you get roughly the same level. However, you've gone down 2 to the 2 level of generation, so 4 times less. So the big takeaway here is that as we build these systems out, and accuracy is very, very important, we're going to be aggregating a lot of information. And inside of these huge data sets, you should be able to figure out how difficult one question is versus the other. Not all questions are created the same. So what this graph is showing you, and if you take nothing away from this talk, it would be this. This graph is showing you that with difficulty as a given into our response, you're able to be so much more efficient with your compute that you can get the same level of accuracy with 4 times less resources. And in terms of competitive advantage, this is something where if everyone can have the same level of performance and you can do it 4 times less costly than the other people, you are always going to win in the long run. So I believe I'm at time here.
Yeah, we can have a few questions if anyone has any.
So is it easily implemented? Can some of our libraries say, here's Grok, you incorporate, we now run the cloud 4 times cheaper, go at it. Now even cheaper, faster.
Can it be coded? 100%. But I think your question is also, where is the difficulty, right? You can give a talk on it and you can explain it from a high level, but where are you going to really make your money here? And in my opinion, the big piece are these process reward models. If you're going to have your model go off in the wrong direction, that's very, very costly. If you're able to have this model catch those mistakes for you at a very, very consistent accuracy, that is very, very valuable.
So, practically speaking, the algorithm is some there. Do you know if there's some model that does these?
So this data set, PRM, Process Reward Model 800K, that is open source. So anybody in this room could decide they want to build a model and use that specifically. And then in terms of architectures or anything else on top of this, I'm not aware of that at this moment. And then the second piece, and this will be the closing statement here, is that for difficulty, that's something that you can really spend a huge amount of time going into. And this is something that will change both based on the model that you're using and then also based on the kinds of questions that your model is meant to answer. So process reward model is very, very important. It's the bedrock for understanding a lot of these strategies. But then to get these kinds of cost savings that you're seeing here, you would really want to understand your users in a very, very deep way. So you can, in this case, segment their questions into different levels of difficulty. That is perhaps step one, train the process reward model. Step two would be understand the difficulty so that you can be very, very precise as you expend these resources. And with that, thank you very much.
Thank you, Matt. It is showing separate. And you want to mirror it. Go to your settings. No, click that. Yep. The reason I was doing this, don't you want to do extend? I think it's extend. And I can see that. Oh, you want to do that? So just I'm getting a new one tomorrow or the next day. Oops. But if it doesn't work, I'll just use one. It's fine. I'll just leave the lines. Alright, whatever. YOLO. Here. You want to back? Hey everyone.
Hello, mic check, yeah. So that was a great talk. Mine is like the cartoon version of that. So if you guys don't want to use brain power, welcome to my talk, okay? My name is Orlando. I moved to Austin 9 years and a month ago precisely. Moved from London. I'm born in Italy, but my dad is Greek, so I'm a weird mixture of European. And so this is my, it's a talk about function calling. How many people here have, how many of you know about function calling? Okay, half the room. Okay, that's pretty good. This is what we're going to talk about today. How did we get there? Why it matters? Et cetera, et cetera. So let's see. So applications are evolving, right? Like if you all been developing for the last 20 years, 30 years, you probably heard of APIs. But the big problem is that LLMs, they can't use APIs, right? And so how are applications evolving and what can we do now that we have AI? Well, we'll discover it today. This is an interesting quote from JP Morgan. He said this stuff, let me see if I can read it. During many prior periods of technological innovation, there have been predictions of tremendous job losses. And broadly, what we have seen is the opposite, driven by increased productivity, lower prices, and also entirely new products and services. So basically, everybody's speaking about how the AI revolution is basically going to, cause job losses. But if you look at when Excel came out many years ago, sure, some people lost their job, but then other jobs were made because suddenly the cost of doing analysis was suddenly lowered, and so many more people got into doing analysis. Whereas people were doing bookkeeping and adding numbers together, suddenly lost their job because you could do it with Excel. And so it's while one thing went down, the other one went up. Some people might disagree with that, and I'd love to talk to you after the talk about job losses. It's one of my favorite things to talk about. So how we got there? Well, hopefully the text is readable. So we started, with the first type of APIs. That was about in the 60s and the 70s, maybe even the 50s, if you want to go back to the first type of mainframes, right? So you could connect directly to a database, send it data, receive data, right? Then we invented personal computers. And so like when Windows came out and all the other operating system, people developed this like operating system API so you can build additional applications to run on your computer. And then the web era, who cannot, can you all relate to the web era? I guess we were all alive during the web era here. So loads of like APIs were built connecting services over the web. And then of course, with the cloud and mobile, that exploded much, much, much faster. The question is, what's next, right? Now that we have like the AI era, it's kind of got here, are we gonna see many more APIs? Are we gonna see, well, the answer is both, yes, right? Because there's gonna be more API calls, but also we're gonna need function calling because right now, and maybe that's gonna change in the future, but LLMs cannot use APIs straight out of the box. And so you need to like kind of encapsulate any kind of API call in this thing called a function call. And then there's going to be a lot of more devices, right? Like smart cars. We've seen like Elon Musk, a couple of blocks from here, right? He's building all these smart cars, and then there's going to be many more smart devices. And so if you followed the news, Meta has actually partnered with a lot of these companies like ARM, Qualcomm, and MediaTek, and they're trying to put like the LLMs on chip, on device, right? So eventually you don't have to connect to the internet anymore. You can just have all the LLM juicy stuff directly on your device, and it's going to be way faster for smaller models. And so like this is the AI adoption rate growth from exploding topics. This is basically, the quote was something like, how many big companies, enterprise companies, have seen the adoption rate go up? And so quite a few. It went from like 55 12 months ago to 72 this year. And so if you remember Windows, 95 I think this was, I forget. I used to write text on here, right? Like how many people here use Word at least once in their life? Okay, good job everybody on Microsoft. And so we had like one human writing. You had one device. Life was good. Then this came out. This was around 2000 something. And if you remember Gmail, and everybody was waiting to get their Gmail invite, right? And then everybody suddenly could like write and communicate and store data on servers. All of this was powered by a different type of APIs, very different from this one, right? This was like a web-based API. And then of course this also happened, right? The iPhone, now people are still using APIs. Multiple people have multiple phones, right? Many more people have phones than computers these days. And so even more API consumptions. And of course there's this, like the last thing that happened, like this huge revolution, and we're using even more of this cloud-based stuff. So humans, the multiple devices perhaps, but like the question is like, what's next? And then what? A question I've always asked myself is, then what happens after APIs? What happens? My background, I've worked at the first API marketplace that was ever invented. It was called Mashape. That was like 2013. And we were like the biggest API marketplace. Developers would come to our website, they would search like, how do I send SMSs? And then they would like end up on a page and they would copy code, pay for an API key, and then they would just be able to like send SMSs from their like blog or their website or their platform, whatever. But like 10 years ago or so, I was like, I think this is the end. Like there's nothing is gonna evolve from here, right? Well, I was wrong, of course. And so, whoops. And so now we have this like new paradigm where it's like a human, an LLM. What can we do together? Have you all heard about the word agentic systems or agentic AI, right? It's like everybody's talking about it. Like, what's an agent? Some people don't even know how to define it, right? But to me, an agent, it's like an intern. Like, it can do very few things, but it can do it really well. And the ability for that agent to be successful is based on how you can implement function calling and prompting, right? All right, let's talk about interaction here. How many humans are going to be needed in the future to like do your work? How many devices? How many LLMs? Does that mean there's going to be agents? Well, if I'm not mistaken, there's a guy called Jensen Huang. He's the CEO of NVIDIA. Have you guys heard of NVIDIA? I hope so, because otherwise we're in trouble here. And so the story is there's going to be many LLMs talking to many other LLMs. And that basically is kind of the same thing with agents, right? Where if you have one human that has 100 agents, it can do much more work much faster. So why am I saying this? Because this is kind of this shift, right? Like everybody knows that you can take a photo today thanks to your to your iPhone. Maybe you have Android like myself, but you can still take photos, and they can be amazing. And that's because of the technology, improvement in these devices. Whereas before you had to spend like thousands of dollars to get a really good camera, now it's in your pocket already, and you can basically do super efficient, take selfies, portraits, whatever, everything you want, and it's all in your pocket. And so if we have thousands of LLMs, are we going to do thousands of network connections? And how are we going to optimize these things between them? Well, this is like a slide that I just didn't want to show, so I'll just skip it. So let's talk about functions, right? This is the important part of the juice of the presentation. So function calling are super cool. They allow to give your LLMs superpowers. So this is my screenshot, actually a couple of screenshots from what this is my company, whatever. We're building this like superpowers that you can install with one click. And basically we can give your LLM these superpowers, regardless of which LLM it is. It can be OpenAI, it can be your fine-tuned LLM on your personal server, whatever. And you can just go and install each of these superpowers so you can use them. These are actually the 3 most used ones. Code interpreter, well, code interpreter takes some generated code that you either write yourself or ask an LLM to generate, and then it actually compiles it and runs it, actually executes it. Well, it can be also compiled. Web search, super important, allows you to go and get data from like different pages, do searches, or just scrape content of specific websites. And then memory. If I tell an LLM today, like, hey, I really love Ferraris, I'm Italian, of course, I love Ferraris. Is it gonna remember tomorrow? Well, the answer is probably not. And so with memory, you can actually give that superpower to your LLM. And the cool thing is that function calling are super, super interesting, but they're kind of like complicated to set up. And why do I say that? Well, first of all, you have your application, right, sends a prompt to the LLM, and it basically has to include the definition of a tool or a function, right, so that it can then use that function and then basically return some arguments that will then be executed by you, and then anyway, it's a mess. So this slide here just tells you how much of a pain in the ass it is. So let's go and like dive deep into how a function call works, right? So you write some code. This is your function. This specifically one, I don't know if you can zoom in. I'll zoom in. Whoop, well, nice. So this function here is just basic Python. It's like, given a title and a location or a description, can you tell me where the movie can be seen, right? And so you write this code, and that's pretty cool, but the LLM cannot use this code. It needs more. It needs a schema. So a schema is kind of like, if you're familiar with APIs, it's kind of like an open API spec, but this gets fed to the LLM. Now the LLM, when it reads the schema, it can understand how to basically use your function. And so basically this is how you do it. You give it the schema in this like variable here, tools, and then you have the prompt. And with the prompt, you basically say, okay, first of all, what's the system prompt, whatever. And then you basically ask your question. How? Can you tell me where iRobot is playing in Austin? So what's going to happen next is that the LLM is going to understand that you can request or call a function, and it's going to pass it, the parameters. Here, actually, there's one missing, the API key, whatever. You say, okay, where am I? I'm in Austin. The movie's called iRobot. Then it will call that function. It will execute it, and it will return like Paramount Theater and then maybe an address or something. This is just an example. And so you as the user or the developer, you then have to append that answer back into your message context, right? Like this is basically like a list, an array of like all the messages that have been exchanged between you and the LLM. And then at the end, you ask the LLM to generate that response. And so at the end of all this like drama, what happens is that the LLM will answer something along the lines of, hey, if you want to go and watch iRobot, you can go to the Paramount Theater that's located at this address in 78701, right? And so this is kind of like the idea of function calling is you can bring data into LLMs. If you have trained an LLM, as you're familiar, the LLM is just basically like a brain. It's trained on data. But if you want to give it superpowers, and I call it superpower. Yes, sir. Great. Yes, there's a follow-up slide about that. It's basically, yeah, it both end up giving more data to the context, so the LLM knows how to answer. So yes, but it's different, right? Like you can pass functions to the LLM to like give it data, but you can also pass function to execute actions. That's the difference. Whereas with RAG or anything like that, it's mostly like, how can I find more information to give a better answer to the user? Some of the use cases that I've been seeing users on my platform is like doing research for sales. So what they do is like they build an agentic system that goes out there, scrapes like websites. And by the way, my mouth is super dry. I feel like I'm on like LSD or something. I was never, by the way, I've never used LSD. Damn. Okay, and never mind. I'll just. Okay, sorry. So for sales, as I was saying, yeah, people basically go and like browse the web with these agentic systems. They scrape data, they give it back to the LLM, and then they give it like even more like workflows and stuff like that. And then finally, like I actually fucked up the other day. I used my own project and I asked, hey, can you do some research? And then my agent ended up emailing the person that I wanted to get in touch with without my consent. And so it emailed like 3 pages of text, and I was like, no. And then I basically lost, that person forever, after a cold interaction. So be careful of AI agents. It's really scary. So isn't it just RAG? No. But kind of yes also, It's just with function calling, you basically have all these like external function that you can get data from, but you can also, oh, thank you so much. Wow. Round of applause for this.
Thank you, Chris.
Samaritan. Thank you so much. Oh, so much better. Thank you. Should have prepared for this. And so I was saying, like, isn't it just RAG? No. And can they be used together? Yes. That you can use them together. So you can do, like, balance them and, like, find whatever works for you, right? And RAG is kind of complicated. It's a total different topic. There's so many ways to do RAG. There's so many implementations. It's actually really scary. I had a friend actually trying to solve this problem, but he failed. Anyway, we talked about this. Yep, sorry. This is kind of like the high level, model. If there's something you need to remember about function calling, it's like you have your application, then there's some kind of runtime. You can connect to different services, whether like, your own services. So if you're an enterprise and you have like databases with loads of data, or like maybe like a fraud analytics system that already runs, you can connect that to your application and to the LLM through function execution or function calling. And why should you care? Why are you here? I mean, why are you listening to me? Well, today, you're building a new IDE. Maybe you're like Cursor or someone like that. But in the future, you're going to build a whole new software engineer. And you can do that with function calling. You cannot do it without today. And so this is kind of where I'm kind of wrapping up my presentation. If you remember where like Claude was, and they were like, hey, how many R's are in Strawberry? It couldn't compute it. But if you actually wrote some Python that would take a string and then figure out how many times the letter R was in that string, and you executed that code through a function call, then you would have actually gotten the right answer. Same thing with ChatGPT. You're like, hey, ChatGPT, can you send an email? Well, no, because it's an LLM. If you don't have a connection to a service that can send the email on behalf of the user, then you're cooked, man. Like, and then the same thing with like, this is Llama. I was like, hey, Llama, can you remember this memory? Like, I really love Ferraris. And then I come back the next day and run, my what's it called? My local host Llama model running with Ollama. And it just didn't remember. And so that's the power of function calling, in my opinion, right? This knowledge cutoff, everybody has seen this at least once if you use ChatGPT. And so to write function calling is really complicated. Depending on what you do. Like if you do the code execution, it's like basically a sandbox that can run any kind of code and return an output to the LLM. You don't want to have people try to escalate privileges and do nasty shit in your actual server. So that's why you kind of like connect it to an LLM via an external service, right? Through a function call. And so my company, Toolhouse, I'm the co-founder here. We're trying to make it really simple by giving you all these like functions already kind of pre-built Whether you're like using public function, like, oh, I want a scrape thing, or I want memory. But maybe you're at a company, like an enterprise, and you have like your own like 1,000 microservices. And we want to make it super simple that all of your engineers can basically implement function calling. So we're trying to do it with 3 lines of code. These are the actual 3 lines of code. This is Python, by the way. We also have a TypeScript library, but you basically import our library, and then you give the knowledge of the tools that you installed on the UI to your LLM, and then the magic happens with th.run tools. And that's when your LLM is now getting that knowledge for free, basically. All right, let's dive quickly into this, and then, yeah, I'll probably skip this. I already talked about it. So the idea is that just like APIs, and I used to work at, like I said, like one of the largest, if not the largest, API marketplace in the world. I actually met the CEO of Postman when he was still like a Chrome extension. Have you all used Postman before to build APIs? Yeah. So me and Abhinav, we were like talking on email like 2014 or something like that. And we're just like, this API thing is pretty cool. And we're like, yeah, we both agreed. But today, again, and this is the most important thing, is LLMs cannot use APIs. That's the thing I'm trying to share tonight. And so we need someone to run, build, and manage these function calls. And hopefully that's going to be me. And one day you'll be like, hey, I know that guy. Or maybe not. Maybe my startup will die. But the idea is that we want to make it super simple for anyone to use function calling. And so if you're familiar with the App Store experience, imagine if you have your own App Store for your own company with your own functions that my tool basically produces for you. And then you just go and install them and then write your own code on top of it, which is actually easier. So that was me. Thank you for listening to my silly story. Sorry, I wasn't as exciting as the previous one. If you want to sign up, I'll personally onboard you and give you $150 worth of credit to test out our platform. We're also hiring. So I raised a bunch of money to hire people. So that'd be pretty cool if you want a job. I don't know, maybe just chat. If not, just make a friend or go out and have some barbecue. I don't know, whatever. And then the other cool thing is, thanks to like people like Jake, we are doing actually a hackathon. So it's hosted at Cloudflare. If you want to show up, just scan this QR code that I took from Google Chrome. And yeah, and I'll say the last thing about hackathons. When I was working in London, like 13 years ago, I don't even remember how long it was, I was basically sad. My life was so sad. I used to work at one of these huge consultancies. No one gave a shit about me, and probably still don't. But one day I went to a hackathon with a friend. It was my first hackathon. It was hosted at Bloomberg HQ in London. And that day, I got a job offer. Like, I'm not going to lie. Like, it was insane. So I quit my boring consultancy job, like Accenture or whatever, and I basically joined a French company. We were building, like, email infrastructure for European people because, America is so scary, right? Like, GDPR, all this crap. And so from there, I just worked at startups forever since. And I got lucky. I worked at another startup before where I was a co-founder, and this is my second one. But the reason why I'm telling you this is like hackathons can literally change your mind. If you've never been to a hackathon, you should go. Whether it's this one, that's now no longer available to scan, or if it's the meta one, or maybe one of the hackathons that AITX has been organizing, like it will literally change your mind. You'll make friends, you'll learn new things, you literally feel like the pressure of like presenting in front of big audiences. So if you're kind of scared or if you're not super motivated to talk in front of big audiences, that's gonna like force you to do that. And then you might get a job out of it or at least some friends. So do go to hackathons, and thank you for having me today. That's my life story. Thank you.
Thank you. All right, everyone. So you're welcome to stay here for until 8:45 p.m. And if you haven't already, please become a member on Austin Deep Learning. So we're nearing 4,000 registered members on Meetup. Or actually, leave that up for a second if anyone needs to do that. Okay. There's a lot of stuff going on this month in Austin for AI. I think it's because the weather is nice this month. So MLOps World is going on in just a couple days, November 7th through 8th. They're not affiliated with this or anything. I just found out about them, and I thought this would be cool for y'all to know that this is going on here. Other people are actually like booking hotels to go to this, so y'all get a save on that. So yeah, check that out. But yeah, if you have any paper that you've read or even wrote that you'd like to give a talk on, or anything that you've built that you'd like to give a talk on, please come see me. I'm wearing a pink polo. I don't think anyone else is. So actually, Ramon, we're both wearing pink. Right. No, yeah, but just come up to me or Ramon. He's also wearing pink, and just say, hey, you want to give a talk, and I would love to have you. So again, you don't have to be the person who wrote it, but if you found some interesting insights or you want to give a talk on it, and these are also recorded, so you can also use that to build up clout on whatever thing you build the cloud on. And also thanks to Capital Factory for always being a great sponsor and giving us a venue to host these events. So thank you, everyone. I have a parking validation if you parked in the garage. And even I think a partial, like even if you get here earlier, it still works. I just can't say that, right? No, I'm saying I can't say that it's the case. If it works, it's great.
That's what they told me to say, basically.
Yeah, that's what they told me to say.